Nicholas Steno was a Danish scientist who studied anatomy in the natural world. And in his studies, he began to question some of the truths of science of his day. For example, he took an interest in the formation of fossils and the layers of rocks that they are found in. At the time, people had often mused about the origin of what they called tungstones that were found in the rocks. One explanation was that they fell from the heavens. Another was that St. Paul had condemned all of the snakes and caused their tongues to fall out and turn into stone. Now, it should be pretty obvious what these actually are to us, but at the time, many people had not actually seen the animals or thought of the connection to what they actually were. Scientists thought that they just grew in the stone, that fossils were natural formations of the rock that just happened to look like things, uh, happened to look like other things. But Steno wasn't convinced. It was when someone sent him a shark's head to dissect and study, he realized that the shark's teeth matched those tungstones. But he wondered, how could an animal that lived in the ocean have parts that wound up in rocks that are now above sea level? He realized that there was a connection between the rocks that these fossils were found in and the way that sediment today is forming. Geologists have a saying now that the present is a key to the past. By observing things happening today, we can draw conclusions about what's happened in the past using the rock layers themselves. So he proposed that these layers of rock that found these fossils or have these fossils were actually once just like the sediment that's forming today. Layers of mud or silt and sand that eventually would turn into stone and then somehow be pushed up onto dry land. To better organize this, he began to look for ways to figure out which layers of rock were older than others. He would develop his ideas into what we now call as Steno's laws of stratigraphy. Now, stratigraphy is just studying the rock layers. His first assumption that he made was that all sedimentary rock is laid down in flat horizontal layers. There's nowhere on Earth that sediment is deposited any way but flat, with the rare exception of something like sand dunes in the desert, which are deposited on slopes. But for most rocks or most sediment, it's deposited flat and horizontal. And that something must have changed the orientation of those rocks over time. But all sedimentary rocks were originally horizontal. And that was his first rule. Next, if those layers have others that are on top of them or below them, the oldest layer had to be laid down first at the bottom of these formations. So the oldest layer is always on the bottom if they're flat, horizontal, sedimentary rocks. For this reason, we often generalize that the further down you dig in layers of rock, the older the rock is, generally speaking. So this is the law of superposition. But not all rocks are sedimentary rocks. We have some that don't behave the same way. Sometimes you might get an igneous intrusion like what's depicted here in this picture. Igneous rocks are from lava or magma and can melt up through rock layers that are already there. Other features like a fault line where rocks have been broken and shifted also cut through the rock layers that are already there. We call this relationship cross-cutting. And if a feature cuts through other layers, then that feature must be younger than the things it cuts through. And we also noticed that sedimentary rock layers should continue throughout the deposit. That Horizontally, they should continue until something blocks their deposition or they were acted upon agents of erosion that appeared after deposition took place. This one doesn't really affect our relative dating process, which we're going to look at here in a second. But it is an important thing to note that not every layer of rock exists everywhere on Earth. They are limited to the depositional environment that formed them. In the image here, we have layers that were deposited at the bottom of a lake. Of course, that lake is not going to exist all over the world, and that deposit that's at the bottom is not going to continue beyond the depositional environment of that lake. All right, so this is kind of a hard concept to get if we just look at the diagram itself. So looking at this, there's a lot going on. We've got some flat layers, we've got some layers that cut through things, we've got a fault line, and we've got layers in the bottom half that are tilted. There's a lot going on in this image. But if we break it down into multiple steps and look at how these layers would have formed, I think it'll make a little bit more sense. So watching this animation, keep in mind that what's happening follows Steno's laws. We start out with limestone being deposited in the bottom of an ocean, which is then topped off by layers of conglomerate, maybe a river or stream started to empty out there. Then on top of that, we have sandstone being deposited. Again, sedimentary rocks deposited originally in horizontal layers. And each rock represents a different depositional environment. How the environment changes is recorded in these layers of rock. Siltstones and sandstones are usually deposited on deltas or slow-moving water. Limestone is deep ocean water. So the environment has changed when each of these layers was deposited. But notice that all these sedimentary rocks are laid down horizontal to start with. If we shift the diagram down a little bit, maybe the rock layers actually subsided or sank, and more deposition occurs on top of that. But remember that deposition is not always constant. If the environment changes and deposition stops, then erosion will take over and actually erode away the rock layers that were deposited. Now here we have a magma intrusion. Magma is hot, of course, and it can melt through the layers that were already there and then solidify into rock like granite. Notice that there are pieces of the rocks that were already there that have been added inside those. We call those intrusions. Now the rock layers are being tilted. Notice that erosion keeps the surface pretty much flat and erodes away. Next, we have a fault line that is cut through and shifted the rock layers on the left up. Again, erosion cutting everything off flat on the surface. So we've got some layers missing and things have changed quite drastically. If deposition starts again, we get flat layers once again. And geologists call this an unconformity, where slanted layers are underneath horizontal layers. Again, we have deposition occurring where environments are changing. Deposition may stop, which erosion then will erode away that flat surface at the top. Then deposition can start again, and we get more layers building up on top of that. Now we have yet again another igneous intrusion pushing its way up through the layers that are already there. This one actually breaks the surface and forms a layer of lava at the top, while the rock that's below ground takes a little longer to cool and forms something like granite. And then again, we have erosion that cuts away the surface features. Erosion can completely erase layers that were here at one time. Okay, so now we can look at this final diagram and piece together the story that it tells. We can use our laws of stratigraphy, that superposition and cross-cutting and law of original horizontality, to put these layers into their relative order, youngest to oldest. So take a moment and see if you can list these in the correct order from youngest layer, the layer that occurred last in the animation, to the oldest layer, the layer that formed first in the animation, and put those events in order. Be careful not to forget that this fault line occurred that shifted the layers on the left and right of that fault line.